Okay, so thank you very much for this invitation to talk at one of these Newton 1665 seminars. So in this half an hour, we'll talk about the connection between the Muon g-2 and the electroweak precision test, and in particular with the running of alpha, delta alpha, in particular the Adoni contribution to the effective running of the effective QED coupling constant. I will organize the talk like this. It will, the mouse, here it is. I will briefly mention the recent theory progress in the Muon g-2, and there has been a white paper put out by the Muon g-2 theory initiative just a few months ago. So I will highlight a few of the main changes that occurred. Then I will talk about the main point, as I said, the connection between the Muon g-2 and delta alpha. And then I will very briefly, just at the end, mention quickly the Muon E project for an experiment at CERN. So I really cannot get rid of this comment. I tried to get rid of this banner, but I don't manage to. Finally, I did it. Great. Okay, so, well, we are waiting for the number, for the Muon g-2 number. We still have the very old one. Here it is. And the answer.
We can't hear you. You are muted. Okay.
Oh.
I unmuted you.
Okay. Now you hear me?
Yes.
Now, okay, perfect. So this number is has an uncertainty of 63 in 10 to the minus 11. This is the number that we have to have in mind when we compare with the theory prediction. We will have a new number very soon, hopefully very soon, and this number will have a very similar uncertainty. It is the result of the analysis of run 1 of the Fermilab experiment. Fermilab already took the first data sets and is expected to release very soon the analysis of the very first one with the precision which is supposed to be the same and roughly the same as the BNL one, the Brookhaven one. There is another experiment, the J-Park experiment, which is a phase 1 proposal with a precision comparable to the Brookhaven one. But the goal is to go down to an uncertainty of 16 in 10 to the minus 11. So a very, very precise prediction, precise measurement, and therefore a precise prediction is needed on our part, on the theory side. Let me just remind you the developments that occurred recently, and these are the numbers from the white paper, as I mentioned, that appeared from the Muon g-2 theory initiative. It's a paper that we put out on the archive just a couple of months, 3 months ago, and it's a thick book, and here are just some of the highlights. The QED contribution did not change. It is still the same, roughly the same number. The 1, 2, 3, 4, 5 loop contributions are here, as you can see. They are, of course, all relevant. The 4 loop is crucial, is 400, 380 in 10 to the minus 11, so it's much larger than the experimental uncertainty. Now this contribution has been checked, many contributions have been checked and double checked. So we have even the analytic result by Stefano Laporta in 2017 for the mass independent term. The 5 loop contribution is much smaller. It's 5 in 10 to the minus 11. So it's really not crucial for the comparison with the experiment, neither now nor probably in the near future. The value that we have is the number that you see here. There is one uncertainty, which you can see larger than the other, and it's essentially the uncomputed term at 6 loop. So this is an estimate, 10 to the minus 12, as you can see here, is the error attributed to the fact that we do not have a calculation at 6 loop. But 10 to the minus 12 is totally irrelevant, okay? 10 to the minus 12 is to be compared with the 16, 10 to the minus 11, so absolutely negligible. So no news here. The electroweak contribution, also this has been in very good standing for a long time, and it's still the same value that we have since in for the last many years. There is a tiny uncertainty here, and this uncertainty essentially comes from the hadronic uncertainties. Hadronic uncertainties in the electroweak loops, you see them here, right? You see a gamma and a Z. These are weak diagrams with hadronic effects inside. So this is a very, very small uncertainty, 10 to the minus 11, again, not going to influence our comparison with the experiment. Of course, the big deal is, as always, in this discussion, is the hadronic contribution, the leading particular contribution to the Muon g-2. This, as you can see here, is originated by this diagram here. Here we have the vacuum polarization, and of course, this has to be computed at very low energy. Therefore, you cannot rely on perturbative QCD. I mean, not everywhere, and therefore you have to somehow compute this differently. And what you do is you know this function is analytic, so you know that you can use a dispersion relation, and you just need the imaginary part of this vacuum polarization, and then you relate this imaginary part to a cross section with the optical theorem. So what you need is which cross section? Well, the cross section will be plus and minus into, well, anything appearing in this bubble, so anything hadronic. So you need to measure the E plus E minus cross section into hadrons at high precision. You see how it is done. It is done like this. This is the hadronic cross section here, and this is the kernel that you have in front, which gives a lot of relevance to the low energy region. So this is really an integral, which, as you can see here, starting from 0 to 1 GeV, already covered more than 3/4 of the overall contribution. These are the numbers obtained by several groups. And as you see, they are in good agreement. And well, there is a number which is in red here. This is the merging of all the numbers, the merging done by the Muon g-2 theory initiative in the white paper I was mentioning earlier. Of course, this number is large, 7,000 in 10 to the minus 11. And as the experimental uncertainty is 60, you want to know this at better than 1%. Better than 1% means that you have to know the additive corrections well. And this is notoriously very difficult because you have many, many channels. And even for the pi-pi, which of course is the leading channel, you need to know these additive corrections well, because what you are doing physics at less than 1%. This, of course, is difficult. Fortunately, there is another approach which has done a lot of progress, which is lattice. From first principle, lattice QCD can produce this number. Until recently, these numbers were not really competitive with the one that you see here, but very recently, the BMW collaboration reached a fantastic result. They produced a result with a sub% precision. Here is the value that they obtained. This is a V2 value. It was slightly different in the previous version. As you can see, this value is very precise. It's less than 1% uncertainty. The interesting point is that there is a tension, however, between this number that you see here and all the other numbers from the dispersive approach. So if this number will be confirmed by other precise lattice determination, there might be a tension between lattice result and the dispersive approach. But this, of course, we don't know yet. I mean, this we have to see in the future. But it's important to stress this fact because until not so long ago, it was the lattice results were significantly less precise, and therefore it seemed that we only had to rely on the dispersive method. But now we have two completely different results, and this is very, very important. If this value from the lattice would be right, then if this result were right, then the tension with the g-2 measurement would essentially disappear. We need to go to higher order contributions, but there are no surprises here. Here there is the vacuum polarization contribution at higher order. You see them here. They have been computed many years ago by Bernd Krause and subsequently improved by Teubner, Nomura, and Alex Keshavarzi, many people, and this is the value that appears in the white paper. So no news here. Also, the even higher contribution, or the alpha to the fourth vacuum polarization contribution, were computed by Steinhauser and his group, and the result was actually larger than expected. But therefore, now the uncertainty that we have here is totally negligible. Then there is the light by light. The light by light contribution, as you all know, it has been complicated. It has had a difficult life. Its value changed many times. These are the latest determination that you can see here, and this is the latest value that appeared in the white paper. This is an important number because, as you can see here, there was a significant reduction of the uncertainty. See, 19 in 10 to the minus 11. This is a very, very small number. So for people who have maybe not followed the g-2 in the last few years, this number might be a bit surprising. This is really a significant improvement due to the data-driven dispersive approach, an approach that was introduced by the Bern group and the Mainz group 4 or 5 years ago, and it really managed to give its many important results, and they are reflected by the fact that the uncertainty went down essentially from 40 to 19, which is a big improvement. So this is not longer the place where you can say, there is always the light-by-light contribution, who knows what happens there. No, it doesn't seem to be the case. This number is has a smaller 20% uncertainty, not more. Also, the lattice, of course, has done great progress on this value, and you see the number here. There is a value recent number from November last year, which is 79 with a slightly larger uncertainty. But I think it's really remarkable. These are amazing results, and considering the amount of work and time that is needed, this is really impressive. So I would say that the light-by-light contribution is not an issue. Of course, it's still a very difficult term, but it's not probably the place where you should look for the discrepancy between theory and experiment. There are higher order contribution. You see them here. It is the light-by-light next to leading order contribution, but it's small. We estimated it with the Bern group a few years ago. It's 2 with a set of 1, so it's really very, very little. Not to worry about this contribution. So if we compare the standard model prediction with the g-2 experiment value, you see this is the discrepancy, 279 with an error of 76. This is 3.7 sigmas. Now, 3.7 sigmas is the usual, I would say, not large enough to claim much, but of course it's large enough not to neglect it. It's of course a very interesting number. And what we asked a few years ago, Bill Marciano, Alberto Silling, and I, was how is this number, or better, the discrepancy, connected with other precision sectors of the standard model, in particular with the precision rhetoric tests? So the question we asked and the exercise we did is the following. We asked ourselves, could it be that this discrepancy is due to some missed contribution in the hadronic cross-section? After all, the cross-section measures exclusively a humongous number of channels, and then they are added all together. Could it be that some channel is missing, some contribution is missing, or even could it be simply that the cross-section is wrong somewhere in the measurement, in some energy regions? I say missing contribution because, as you saw, the experimental value is higher than the theory prediction, and the theory prediction has to increase to match the experimental value. And to increase, the hadronic contribution has to increase. And to increase the hadronic contribution, one has to increase the cross-section that you see here. So we could increase the hadronic cross-section somewhere, or say tomorrow some experimental colleague may come and tell us that they missed a particular contribution somewhere. Then the cross-section increases. You do, once again, the dispersive integral, and you get a higher value of the hadronic contribution to the mu g-2, such as to cancel the discrepancy with the experiment. This could happen, of course. We hope not. I mean, we hope that it is due to new physics, but we asked ourselves, could it be? Well, if you do this game, if you do increase the hadronic cross-section to bridge the Muon g-2 discrepancy, well, then you also touch something else, of course. You also touch another dispersive integral written here, indicated here by the simple letter b. And this integral b is the contribution, the hadronic contribution to the running of alpha. The difference between these two lies in the kernel functions. The input, the experimental input is exactly the same as this cross-section here, but what changes is this, as you see, this kernel function here. This kernel function roughly goes like 1 over s, is the same k that we saw a few slides ago. On the contrary, the kernel g for delta alpha at low energy is essentially a constant. You see, if you remove s, this is just a constant here. So let's play this game for a moment. Let's imagine that the cross-section is increased by a factor, multiplicative factor epsilon that you see here. And where do we increase it? We increase it in some beams, in a beam centered at square root of S naught. Okay, square root of S naught with a width called delta. Delta can be anything. Of course, we can take it wide or small. We can take even the delta to 0 limit, in which case it's just a peak, right? It's a delta-like peak. So what happens? Now, what happens is that if you change the hadronic cross-section, if you increase the hadronic cross-section, you also increase delta alpha. Now, delta alpha is a crucial input of the electroweak fit. And in particular, for many years when we thought of this was 2008, so more than 10 years ago, the Higgs was not yet discovered. Our goal was to see if the prediction of the standard model Higgs would change, and if so, by how much. In fact, the game that was played back then was to take some observable, some theory prediction, in particular the mass of the W or the effective sign, the effective mixing angle, the sign of the mixing angle, and see if the prediction matches the experimental value. The point is that the prediction depends on many parameters of the standard model. Depends on the mass of the Higgs, on delta alpha, the mass of the top, alpha S, and other parameters. So what we did at the time was to change delta alpha, or change the Adoni cross-section, and change therefore delta alpha, and see what consequences this had on the upper bound on the Higgs boson mass. And the result we had was the one that you see in this figure here. This is square root of S naught. As I said, it's where you do change the cross-section, which is a free parameter here. Here it's from 0 to 1.6 GeV. And this was, at the time, the upper bound on the mass of the Higgs from the electroweak fit. So this is the curve that we wanted to change, or see what was the effect of the assumption that I just said on this result. And the effect is the following, is to change this curve, this black line here, into the red curve that you see here. So as you see, the upper bound on the mass of the Higgs changes very much according to where you change the cross-section, the hadronic cross-section. At the time, there was no Higgs, obviously. Now we know the Higgs is here, if the standard model Higgs, but it looks very much like standard model Higgs. So if the Higgs is here, at the time there was no Higgs, but at the time there was already the lower bound, which was here. So this game brought us to led us to the conclusion already then that actually, yes, you can change the hadronic cross-section to bridge, to accommodate the Muon G-2. However, if you do it, you have to do it at relatively low energy, say below 1.5 GeV. Otherwise, you have conflict with the electroweak fit. Well, now many things changed since then. In particular, we discovered the Higgs, and of course, now we know its mass very, very precisely. So together with Alex Keshavarzi, who pushed us to do this update, we decided to redo completely this analysis. And with many changes, of course. As I said, the first one is the fact that now we know the Higgs, and that's a major change. And but not only, I mean, many things change also in the electroweak precision observables. And they are much more precise, and W has an error which is a half of the previous one. Sin² theta actually did not change much, but the top also improved. There has been great updates in the sigma, in the hadronic cross-section, theory improvements. So we decided to use a global fit this time. Earlier, we were just using two predictions, the mass of the W and sin² theta effective, the effective electroweak mixing angle. Now we use only these two. We were using only these two. Now we use the global electroweak fit, which, as you see here, has all these inputs that are listed here. In particular, we used the g-theta to do this analysis. And the result of this is the following. So this is the present value that we obtained, the 2020 result that you obtain. As you see here, so this is the prediction for the Higgs mass. The center value is around here if you do not touch the Adoni cross-section, but if you start changing the Adoni cross-section to bridge the Muon G-2, then this is what happens to the central value. The central value, as you see, decreases. This is the +1 sigma, ±1 sigma, and in pink, you can see the 95% confidence level. So, as I said, many things change. First of all, it's clearly visible here. Now we have a Higgs, which is essentially a line. I mean, the uncertainty is there, but you cannot see it. It's 140 MeV, so it's nothing. The W mass, I'm insisting on the W mass and sin² theta effective because these two are really the two leading quantities that are calculated and matched with experimental values, okay? All the asymmetries are transformed into sin² theta values. So the sin² theta value improved, but very little because, I mean, there have been measurements from the Adoni machines, from Tevaton and the LHC, but the central value has been pretty much the same and the uncertainty is also the same. On the contrary, the MW change very much. The value went steadily down in the last 10, 15 years. If the value of the W goes down, the Higgs prediction goes up, which is good because it was too low before. And this is what we have nowadays. Also the top, of course, it's much more precise. So as you see here, this is the 95% confidence level. If you go above, say, 0.7, 0.8 GeV, then you start to have a conflict with the electroweak fit. So the upshot is that, yes, shift of the cross-section, hadronic cross-section to fix the Muon G-2 are possible, but you have a conflict with electroweak fit if they occur above, let's say, roughly 1 GeV to be conservative, 0.7, 0.8, or let's just say 1 GeV. Now, therefore, you can just say, well, they may occur at lower energies. Yes, this is a possibility, of course. They can occur at lower energy. So we focused, in fact, on the region below 1 GeV. And here is the result we have. How much do we have to change the cross-section if we do the shift below 1 GeV? So in this plot, you see the percentage here is the percentual shift of the cross-section when we integrate, do a shift in a uniform range between the threshold here up to, well, the value that you see here. So for example, let's restrict below 0.7, which is the value that I was telling as a reference before. If we want to change the cross-section from threshold to 0.7, well, we have to change the cross-section by, well, here it is, say 6%. This is the blue line. The blue line tells you by how much you have to change the hadronic cross-section. The minimum of this curve is obtained if you shift the whole cross-section from 0 to infinity, but of course this has no meaning. I mean, this would mean to shift even the perturbative QCD result. Of course, this means nothing. It's just to have the reference value, which, as I said, is 4.1%. In this plot, we also show with the red curve what is the percentual variation that you would need to apply, not to solve the Muon G-2 discrepancy, but to solve the discrepancy between the dispersive results and the value obtained by the BMW. I actually apologize because this is the value in our paper, in our published paper, but in the meanwhile, as I said, the V2 of BMW changed a little bit the value. So this red curve is now a little bit lower than what is plotted here. It's not yet updated, this figure. In any case, what I want to emphasize here is that these shifts are large. Actually, they are very large. For example, here, the black curve that you see here indicates the integrated precision that you have integrating in the same bin, right? And this integrated precision, the quoted one, quoted by the experiments, is, as you see, below 1%. Therefore, a shift of several percent that you see here seems unlikely because, or at least it's in conflict with the quoted experimental precision. And okay, you can claim that if you go to very low energies, then you have an uncertainty which is larger, but as I said, the required shift then is even higher. So this is really not looking likely at all, but who knows? I want to mention very briefly, I see my time is almost up. So what happens to we wonder what happens to the electron G-2, because as you saw, it is also very, very precise. And there is a discrepancy also there, which is only at 2.5 sigmas, by the way, with the opposite sign. And this doesn't look like a naive scaling of what happens in the Muon G-2, because if you do a naive scaling of the Muon G-2 discrepancy, you get a 10 to the minus 13 discrepancy, while here it looks more like a 10 to the minus 12 discrepancy. It looks much larger. And this is important, as we pointed out several years ago with the Paradis and Giudice. I mean, there is only an experimental limitation in using the electron G-2 to test new physics, because it's only a matter of improving, of course, this is a very difficult measurement, but it's a matter of improving the measurement of alpha and of the electron G-2, because the theory is ready. As you see here, the uncertainties for the theory are at the level of 10 to the minus 14. So you may wonder what happens to the electron G-2 if I play this game on the Muon G-2. And the answer is not much. because, well, it doesn't improve it. It makes it slightly worse because it goes in the opposite sense. But the shift is small. You see, this is a shift which is typically of the order 10 to the minus 13, while the discrepancy is 10 to the minus 12. So the tension is already 10 to the minus 12. You only add a 10 to the minus 13. So not much happens here. What is more interesting is the ratio of the electron and muon Adoni contribution, rescaled here by this naive scaling in order to keep it close to 1. This is interesting because there is a recent result by Giusti and Simula on the lattice, and which is rather precise. Therefore, you could actually see, if you play the same game, you modify the Adoni cross-section, you look at what happens with the ratio RE mu, and you see that you obtain this red curve here. Unfortunately, the precision is not yet, the precision of the lattice is this blue band. It's not yet precise enough, but if it would decrease a little bit, then we could perhaps put some bounds, oops, I'm sorry. We could put some bounds on this region here at low energy, which, as I said, is the region that we cannot access by the other remarks that I made earlier. So this could be an alternative, or better say, complementary issue that would be interesting to study. I conclude this section mentioning that there are 3 recent papers on a very similar topic. As you see, the titles are very similar. One is by Crivellino, Richter, Manzano, and Tool, one by Eduardo de Rafael, and the latest one just a month ago by Bogdan Malescu and Matthias Scott. How much time do I have? 5 minutes? Less?
3 minutes.
3. Okay, in these 3 minutes, I will tell you that there is fortunately a possibility to determine alternatively the Adoni contribution to the mu and g-2, which is neither the dispersive one, neither the lattice one, but is the fact of using a scattering space-like method. The idea is very simple. Instead of using this relation that we showed, that I showed earlier, which is called the time-like expression, you can just invert these 2 integration and you get this expression here. This is certainly not new. This expression was computed by Lauto, Peterman, and de Rafael in the 70s and used by our lattice friends. But we realized with Carlo Carloni, Luca Tentaduro, and Graziano Melanzoni that it could actually be used with the scattering data to extract a mu from scattering data. We identified the process which sounds most promising, which is muon electron scattering. Also in particular because there is a muon beam at CERN, 150 GeV muon beam at CERN, which is exactly at the energy which would be interesting to study the mu and g-2 contribution. The idea is very simple. You scatter a beam of muons on beryllium targets. They should be thin in order to have, and many of them, in order to have a large cross-section, luminosity, but also the thickness should be little because you want to avoid the multiple scattering. And then you do a very precise measurement of the angles with these thin silicon strip detectors. We sent a letter to SPSC last summer, and the test run was approved very recently. If you only look at the statistics with the beam as it is, with the 2-3 years of running, one could reach this luminosity here, which translated would provide a determination which is with an uncertainty of 20 in 10 to the minus 11. 20 in 10 to the minus 11 is comparable or better than the present uncertainty of lattice and dispersive approach. The problem here, and of course it's a big issue, is the systematic. The systematic effect should be known at better than 10 ppm. And this is of course extremely challenging, both experimentally, but also from the theory point of view, because you have to compute ratios of the cross-section at 10 to the minus 5, which is of course extremely complicated. But we are working on that. And as theorists, we still have a little bit of time to catch up with our experimental colleagues. These are my conclusions. The conclusion is that the question that we addressed is if the discrepancy of the mu and g-2 could be due to missed contribution in the Adoni cross-section. The answer is yes, it is possible, but this should occur at relatively low energy, say below 1 GeV, because if this occurs at higher energy, well, then you have conflict with the electroweak fit. On the other hand, if you think of shifts in the cross-section, the Adoni cross-section in the region below 1 GeV, well, then you have conflict with the quoted experimental values and errors of that the experiment give for the cross-section. The many experiments give for the cross-section in this region. There are effects on other observables. I mentioned the electron g-2, the ratio mu. We also had a look at the sin squared theta at low energy. They are not yet competitive. If this discrepancy beyond the discrepancy of the Muon g-2, if a discrepancy persists also between the two different determinations, meaning the dispersive timelike and the lattice one of the Adoni contribution, when then Muon will provide an independent determination, which is space-like and completely alternative, as I said, from both of the two. Okay, I'll stop here.
Thank you for a clear talk. So are there any questions?
So maybe I have a question.
Yes, Luca.
Assume that the experimental value of g-2 will be confirmed by the experiment, and
Yes.
Assume also that the lattice BMW result is correct. Then what you conclude is either that the experimental value of sigma has some systematics. I guess that's the most likely interpretation. But the question is, can you imagine some new physics below 1 GeV that affects this cross-section?
This is a good question, and it is exactly the question that we are thinking of in the last few months. Okay. I don't have an answer. Okay. But of course, you would have to think of something that affects. Of course, when you measure the Adoni cross-section, your experimentalist colleague tell you a number, and this number, for example, if it's pi, you don't know if that pi has new physics inside or not. The final state is pi, and that's it, right? Whether it is mediated by what, you don't know. So that it's automatically defined as Adonic contribution. Whether it contains new physics, you don't know. And that would not help, of course, because it's already called hadronic, and the discrepancy is there. So, of course, you could try to think something in different final states, and that is more interesting, perhaps. If you could think of different final states which have not been identified, and they could perhaps give a contribution. But it's very difficult because we are playing in a region which is this low energy region, which has been measured by several collaborations. So it's not easy.
I see. Thanks.
Any more questions?
Yes. Question from Lelouch, please.
Yeah, hi. Hi, Massimo.
Hi,
thank you for the very nice talk. I did have a question concerning Malaescu's paper, whose conclusion seems to differ somewhat from yours. I guess not fundamentally, but they find that if you assume that to explain the g-2, you only have to modify the Muon g-2, you only have to modify sort of the low energy end of the spectrum. Then, I guess, as you said, you have no tension with the measurement of delta alpha at mz squared. So I guess it's quite close to your statement, in that if you really limit yourself to below 1 or 2 GeV, there is no problem. There is only really a problem if you say that you're somehow modifying the whole cross-section to...
I totally agree with this, actually.
Yeah.
I remember the paper by Bogdan and Matthias. Okay, in this respect, I don't think we reached a different conclusion. Maybe they had more of an emphasis on the correlations, if I remember correctly. They studied in detail the correlations, the correlation of the uncertainties. which we also did, but somehow the paper maybe has more of an emphasis on this. But if I remember correctly, their conclusions were that indeed, in this respect, were quite similar. I mean, if you restrict yourself to a low energy region, I don't remember which number they were quoting, but I said 1 GeV in the paper. We had the exact number that we get from the FIT, which is 0.75 GeV, but this essentially is the same. I mean, we are not really picking on the precise value. This is, by the way, the value that we get from the Higgs mass. From the W mass, we have a slightly higher value. The Higgs mass is just more sensitive, so that's why we quote that number. But I would say that in this respect, we had similar conclusions.
But also many of your graphs are 95% confidence level graphs, which is not a very large deviation.
Yes, this is true. This is true.
I mean, if you know, sort of say you can stretch things a bit.
Yes, absolutely. I mean, for example, this figure here, which is our main figure, probably main result, if you stretch it and you put it, so 1, 2, 3 sigmas, you see the curve would increase like this. Mm-hmm. So this would go certainly higher, above 1 GeV. Mm-hmm. That's maybe why I quote 1 GeV to be conservative, while we would have 0.7, and if you go to 3 sigmas, it would perhaps be, I don't know, 1.2 perhaps, if I look here. Mm-hmm. But it would really not change the essence of what we obtained here, I would say.
Yeah, you're right. It's only the low end of the spectrum that can be affected.
Which also seems to be, if I understood correctly, your plot in your talk that you gave a couple of months ago, it's also seemed to be in agreement with the fact that the excess, the difference that you have in the first space-like beam at 0.1 GeV, if I remember correctly, right?
It's somewhere like around 2.8% only in that bin. And then, so it's only in the running from 0 to 1 that we see a difference with experiment. If you run from 1 to 10, then you're already in agreement with the dispersive.
Yes, this seems
so
to be very
also
similar.
In the space-like region, it's very, very limited in range.
Yeah, the space-like kernel, of course. Yes, right. If I can also comment, add perhaps an information which now I see in the picture. I did not comment on this. There is this additional dashed dot curve that we added in the latest version of our paper, and this is due to a comment that we received from a few people. Some asked us, but look, your analysis relies on sine squared theta, and many senior people, including myself, remember how difficult it was in the LEP era to have the discrepancy between the LEP value of the forward-backward asymmetry and the asymmetry parameter from the SLC at slack. Well, nowadays the situation has changed. In fact, we have the Tevaton and the LHC value for sine squared theta, which happens to be exactly in the middle of those two values. And you could actually forget of both of these values. And so the analysis is not really dependent on that set of inputs. So you can actually remove them all. If you remove them all, well, if you remove the contradicting one, then you get the same value, because as I said, the hadronic measurement of sine squared theta gives exactly the same central value as before. But even if you remove completely sine squared theta, meaning all the asymmetries coming from LEP, SLC, and Tevaton and LHC, then you get a curve which is this one, which is lower. See, this is a lower curve. So actually removing sine squared theta and all the issues with sine squared theta, the old issues, you actually make the statement a bit stronger than what it was. So we thought to add this to explain that actually there is no issue at all on the sine squared theta value anymore.
All right.
Sorry, I just wanted to add this. It was unrelated with your question.
Thanks again. And